Okay, this video is a bit of information about five geometric constructs: points, lines, planes, and segments and angles. You're going to find things that are derivatives within this, but those are the five major topics here. In any form of geometry, including Euclidean geometry, which is what we're predominantly studying in this class, you get three undefined terms. You get a point, a line, and a plane. Now, generally speaking, we have in our head what these things tend to mean, but they're not necessarily that. So when you move from one form of geometry to another, the image of these things tends to change. So in Euclidean geometry, they have a particular image. In spherical geometry, they have another image. In hyperbolic geometry, they have another image, but they are never defined in any of these systems. Okay, so we tend to visualize in Euclidean geometry a point as a dot, and we tend to name it with a single letter. So we could say that this is point A, or sometimes we could just call it A. A line we tend to kind of view as a segment with an arrow on both ends to give it the idea that it's moving on and on and on forever. And we pick 2 points on that segment, which I'll call it as A and B, and we would say that this is line AB, or we could also say that it's line AB. So we tend to name a line with 2 points. Sometimes we might do something funky here, like draw a line and put like a script letter next to it, and we could call that line K. This happens in this course, so you may just want to be aware that that happens. But the typical naming convention of a line is to use 2 points that are on the line. A plane, which we technically visualize as a flat sheet, we tend to represent in this course with a parallelogram. And we tend to use 3 points on the plane. So you can kind of visualize that as laying flat with 3 points, and we would say that this is plane A, B, C. We could also do something very similar to what we did with a line, and we could just draw an X here in the corner and call this plane X. But it's typically 1 point for a line, or 1 point for a point, 1 letter for a point, 2 letters for a line, 3 letters for a plane. One of the keys to those 3 letters is that they have to be non-collinear. So if you're using A, B, and C, you want to visualize those as not being in the same line, because if you have them in the same line, you could be talking about more than one plane, so that's not a unique identifier. So you want to have at least 3 letters for a plane. Okay, so segments. All right, so when we draw a segment, we tend to have a point, a stretch, and another point. So we would say that this is segment AC, okay? We can write this as segment AC. So notice it's like a bar over the AC with no arrowheads, okay? So that means that we have a segment, it's point A, it's point C, and all the points in between them. Now, no, there's an infinite number of points here. We also call point A and point C the end points of the segment. So A and C have kind of a specific name, namely that they're called endpoints. Okay, so this is kind of the unique identifiers of a segment. Okay, so in geometry, it's not sufficient just to have objects, but we have to have ways of measuring those objects. So we establish what is called the ruler postulate. In Euclidean geometry. And the ruler postulate, well, a postulate, first of all, is something that's a mathematical statement that we can't prove and we don't try to. So, just like an undefined term is something that we don't define, a postulate is a statement that we don't prove. So, so far we've had 3 undefined terms, point, line, and plane, and we've had 2 definitions. We've had a definition of a segment and a definition of an endpoint. So now we're getting into statements about these definitions. And a ruler postulate is a statement that we don't have to prove. It's something that we believe is somewhat obvious. And not only don't we have to, we can't prove it. Okay, so the ruler postulate says this. If I have a line, okay, so I have a line, and I pick some point on that line, and I call it 0. And then I pair another point on that line with 1. Then my argument is that I have now given a numeric value, a real number value, to every single point on that line. Okay, so I've basically created a coordinate system. Why do I claim that I know where all the other points are? Well, let's think this through. I'm going to change color here for a minute and think this through. So if I know that 0 is here and 1 is here, then if I go 1 more, I'm at 2. And then somewhere down here is going to be 3, and if I go in the other direction, I'm at -1, and now I'm at -2, and now I know, if I pick a point at random, so let's use orange, I pick this dot here, I know that that dot pairs with -3/2. And if I want to know where the point that corresponds to 3/4 is, then it's around here somewhere. So given a real number, like pi is going to be out here somewhere. Right? Given a real number, you can find every single point, and given any given point, you can find that number. The key to it is, though, is I need to know where the 0 is. Yep. Sorry about that. I need to know where the 0 is. And I also need to know where the 1 is. Once I know where these two numbers are, I know where everything else is. If I move the 0 or I move the 1, all the numbers move with it. Okay, so that's the idea of the ruler postulate, is I can figure out where points are. Now, the other thing is that if I have that line and I know where the 0 is and I know where the 1 is, then I can find the distance between any 2 points on that line. So let's say this one is at x and this one is at y. Don't know what x and y are, but I want to know how far is it from x to y. Okay, well, the ruler postulate says that I simply take those two values, I subtract them, and I take the absolute value. Now, note, if I do that the other way, it's still the same. So the distance from x to y is the distance from y to x. So the ruler postulate is saying that if I want to find the distance between any 2 points on the line, establish a coordinate system. So that gives me a unit of measurement. The distance from 0 to 1 is a unit. And then I can pick any 2 points on the line, figure out what their values are in that coordinate system, subtract them, and take the absolute value. Now note, when it's an absolute value, this requires that distance and length is always greater than or equal to 0. It's always a positive number. Okay? So that gets me the ruler postulate. Okay, so this gives me something also called the segment addition postulate. And this is a very similar statement, okay? So it deals with the idea of measurement and all of this. It says that, like, if I have a point, let's call it A, and I have another point, and let's call that C. So I'm going to connect those with a line segment. So now I have the segment AC. Okay, and somewhere between those is a point B. Does it have to be halfway between them? No. So let's maybe clean this up a little bit and put point B maybe here. Okay. Now, note, if I want to talk about length, right? So I have segment AB, right? And I want to talk about the length of segment AB. I just write AB. Okay. So that's kind of an important distinction. This is an object. This is a number. This is how far it is from A to B. Okay, so given that, the segment addition postulate says that the following statement has to be true. If B is between A and B, then AB plus BC has to equal AC. Okay, so you're sitting there going like, no kidding. Like, duh. Okay, that's what postulates should feel like, okay? So when we establish a postulate, we should feel like, oh, this is pretty straightforward. I shouldn't have to feel like I have to do any proving here. Why? Because it's somewhat obvious, and I don't have to state that. If I add this distance to this distance, I get the whole distance. That is the segment addition postulate. Okay, so since we have a way to measure things, we have a way to establish a type of equivalence. Now, equivalence between numbers, we're going to use the term equals. When we're talking about equivalence between objects, we're going to use the word congruent. And in this course, equals is going to have the sign just equals. Congruence, we're going to say that it's this, and we're going to put a little tilde above it. So when we talk about congruent objects, we're going to put a tilde above them. Okay, so here we have an opportunity to talk about congruent segments. And we want to know what it requires for two segments to have some semblance of equivalence. Okay, so if I have a segment AB and I have a segment CD, right, and I want them to be congruent, then we're going to say this is true if and only if. So IFF means if and only if they have equal measures. So if they're the same length, then we say that the segments are congruent. Okay? So this gets us to some interesting positions. Like, I now can talk about measurement and I can add in some thinking. Like, I can define what a midpoint is. So let's say this is point A and this is point B, and I want to have a point M, okay, which is the midpoint between A and B. Well, I can define that because, see, if this is the same length as that, right? So if AM is the same length as MB, then M is the midpoint. So I can define the midpoint as the point that makes segment AM congruent to segment MB. So now I've just derived a definition for a midpoint from the definition of congruent segments, which uses the ruler postulate, and so forth and so on. So you can see we're building a system with a firm foundation here. Okay, so we have to start moving toward angles. And in order to get to angles, I have to first establish what a ray is. Okay, so what is a ray? Okay, so if I have a point, let's call it A, and I take all the points that extend in one direction from A. So let's say it starts at A, goes through C, and just keeps going in that direction. This is a ray. Okay, so we have a special name for the endpoint A. We call it the endpoint. Okay, C is just some point along the way. It's not special. Okay, so when I name the ray, I'm going to just make a right arrow. And the arrow just always goes to the right. Even if the ray goes this way, its naming always goes to the right. The first letter, that one there, has to be the endpoint. So we're going to call this ray AC. So I know that it starts at A, goes through C, and in that direction. So a ray is like kind of like part of a line, but not all of it, and it only goes in one direction. It starts at a point and goes in one direction. All the points are collinear. It's wrong to say that this is half of a line, because this is still an infinite number of points. It keeps going and going and going. Okay, a line goes infinitely in two directions, a ray goes infinitely in one direction, but it's not half. That doesn't make sense. So a ray is not a half line. Okay, so, but it starts at an endpoint, goes through one direction. So this is kind of critical. Okay, why is this a critical idea? Because it's going to lead me to an angle. Okay, so something that I want to establish before I get to an angle is that, like, if I have a point, let's call it A, and it goes through C going this way, and it goes through, let's say, D going this way, then we have an interesting situation here. So this, let's say this all forms a line when you join it all together, right? If I have ray AD and I have ray AC, so these are rays going in opposite directions. These are called opposite rays. Now this is the beginning of a thought of an angle, because these two rays have a common endpoint. They both have A as the endpoint. Okay, so what if I drew this where A was the endpoint and I had AD going this way and AC going this way? Okay, so I still have two rays with a common endpoint A, but now they are going in different directions. And not the opposite directions. Okay, so this is an angle. Okay, and we have some names for these things. So point A here in my angle is called a vertex. Okay, so it's a special point. It's the common endpoint of the two rays. Now, the two sides here, so AD being one of the sides and AC being the other sides, these are called sides. So the two rays that make up the angle are called sides. Okay, so you have a vertex, you have two sides. This gives me an angle. So we have some naming conventions here. This angle is typically named by three letters. Okay, so I could call it angle DAC. So notice where the A is. The vertex, that critical point, the common endpoint, is always named in the middle. Okay, so DAC is an angle where the vertex is in the middle. Now note, this is exactly the same as saying angle CAD. these are the same angles. Okay, so these can be like interchanged, not a problem. If you put the A somewhere else, like angle ACD or angle CAD, that is not the same angle because the vertex is always the letter in the middle. Okay, in this case, you could call this angle A. Why can I get away with that? Because it's the only angle A in the frame. Okay, so if I suddenly made like another ray here and called it E, right? So this would be the ray AE. You could no longer use this because now I have 1, 2, 3 angle A's. And if I said angle A, you'd be going, which angle A? I don't understand. So there's an angle EAD in this frame, there's an angle DAC in this frame, there's an angle EAC in this frame, and they're all angle A's. So if you're going to only use one letter for an angle, you got to be really cautious about that. It's done. It'll be done by me, but you have to make sure that you know exactly what angle you're referring to. Okay. Okay, so the tool that we use to measure linear measurement is a ruler. The tool that we use to measure angle measurement is a protractor. So just like we had a ruler postulate, we're also going to have a protractor postulate. So what does this thing say? It says that I'm going to start with a line, okay? And I'm going to start with a line A, B. And in that line, I'm going to put a point O. That's between A and B. And then what I'm going to do is I'm going to create, I'm going to look at this. I have two opposite rays here. I have the ray OB and I have the ray OA. So what I'm going to do is I'm going to have OA point to the value 0. And I'm going to have the ray OB point to the value 180. Okay, that seems like an odd number to pick. But we'll get into that a little bit later on. So OA is pointing to 0, OB is pointing to 180. All right, so all the rays that can be drawn from O on one side of AB are going to point to the numbers from 0 to 180 equally spaced. So I actually have created a sense of unit here. So like if I draw a ray from O out to C, this might point to 60. Or I might have one here drawn out to D, right? So this might point to 120. Okay, so what I've done here is I've built a scale. I can go from 0 to 180. Literally, if you were to draw a curve here, so a bit of a curve here, you would see that you would have a protractor, right? So this is 0, 60, 90 is here, 120 is over there, 145, so forth and so on. So we're literally building a protractor. Okay, so how do I measure an angle? So let's say I have my protractor, right? So I have my point A, I have my point O, I have my point B, and this one's pointing to 0, and this one's pointing to 180, and I come across an angle, right? So this is point C, and here is point D, and now I want to find the measure of angle. So I want to find the measure of angle COD. Okay, so what I do is I look at the number that OC is pointing to. So let's say it's pointing to X. I don't know what it's pointing to, but it's pointing to X. And I look at the number that OD is pointing to, and I'm pointing to Y. And lo and behold, just like the ruler postulate, if I take X minus Y, or whatever, Y minus X, and I take the absolute value, I'm going to get a number between 0 and 180, and that number is the measure of this angle. Okay, so this is how we're going to define the measurement of an angle. Is using the protractor, I figure out what one side of it's pointing to, what another side of it's pointing to, and then I subtract those two numbers. Now, conventional use of a protractor says lay the protractor down so that one side of the angle is pointing to 0 and just look at the other number, because anything minus 0 is that number. So that kind of makes using a protractor a little bit simpler. Okay, so now once we have the ability to measure angles, we can make a statement about equivalence, right? So let's say I have an angle over here. Let's call it angle A, B, C, and let's say that this is an 80-degree angle. Okay, and then I have another angle over here, and let's call it D, E, F, and it's also an 80-degree angle. So I know that the measure of angle ABC is equal to the measure of angle DEF. So I shortened this up. I have that, and this is going to be true if and only if angle ABC is congruent to angle DEF. So in order to have congruent angles, right, we have angles that have the same measure. Okay, so this gives me two additional ideas that I can kind of talk about with regard to angles and terms that I'm going to want to be able to use pretty quickly. I have the idea of adjacent angles. So two angles are adjacent. So let's say we create the situation where I have point E, point F, point G, and point H. This is a diagram where they have a common endpoint, right? And this angle and this angle don't overlap, and they have a common side. Okay, so the common side here is FG. They have a common endpoint and they don't overlap. If I have that, I can say that angle EFG is adjacent or next to angle GFH. So these are two adjacent angles. They don't have to be the same size, but they have to be with that common endpoint and that common side, right? So common vertex, common side. Okay, the other idea that I want to put in here is the idea of a bisector. Okay, so bisector is analogous to midpoint. You have a midpoint of a segment, you have a bisector of an angle. So let's say I have some angle C, let's call it AD. And I draw a ray, right? So this is a ray AM in such a way that that angle measure, whatever it is, let's say it's measure X, and this angle measure is the same. So this means that angle CAM is congruent to angle DAM. So these two both have the same measure, therefore they are congruent angles. If that's the case, then I say that ray AM bisects is the angle bisector, so it bisects angle CAD. So we're CA, not CAC, CAD. Awesome. So we're saying that this ray is the bisector of that angle. Okay, so some summary here. We've covered a lot of ground today. Just want to make sure that we've got this idea here. You have three undefined terms, right? A point, a line, and a plane. Okay, you also have the idea of a segment as like the points in between them. So 2 points and all the points in between them, which got us to the idea of distances through the ruler postulate, and also the idea of a midpoint, right? So we got midpoints from that. You have also established what a ray is, so kind of being part of a line going off in one direction, right? And then we were able to take 2 rays that had a common endpoint and make an angle. So 2 rays with a common endpoint gives me an angle. And then we got the idea that we can find the measure of an angle using the protractor postulate. And we got the idea of an angle bisector. So this is kind of like a quick summary of what we got here today: points, lines, planes, segments that got us distances and midpoints, rays, angles, measures, and bisectors.